So this is the second part of chapter 21, nuclear chemistry. So in part 1 lecture video for chapter 21, we learned about the 5 different types of naturally occurring radioactive decay. So if we have a nucleus who is unstable, that makes it radioactive, then those 5 types of radioactive decay in the last video are the pathways that unstable nucleus has to become more stable. So what we didn't talk about is how to know when each one will happen. I mean, in the questions that we practiced, I told you, hey, this is going to do that, write the equation. So we can handle that. It's if you were to, be walking around outside and you just picked up this radioactive nucleus off the ground, stop it and put it down is my first advice. But if you're like, hey, I want to know what's going to happen to it, how can we predict what would happen? That's what we're going to start this video with. So I'm going to actually backtrack back to Canvas here. So I'm on the chapter 21 page in Canvas, and I'm going to open up the belt of stability file. I'm just going to open up a PDF document that looks like this. I'm going to be referring to the belt of stability for whatever reason. I didn't put a title on this, so this is is it going to let me write on here? No, of course not. This is the belt of stability. I guess it says it there right in the middle, but this is what we're going to be referring to. And so when it's time to work on chapter 21 mastering chemistry, or work on chapter 21 discussion worksheet, or take the exam for over chapter 20 and 21, you're going to want to have this in front of you, and then we're going to refer back to it. But I just wanted to show you where it was. And this version, the one that I made the copy of and put it on Canvas, has a pink fuzzy line, and the one we're going to see in the PowerPoint slides have a yellow fuzzy line. The yellow fuzzy line is the most recent editions version of the belt of stability. I like this one better. It's just cleaner looking and has less random crap on it. So that's why I gave you this one. It's just an older version of our textbook's belt of stability. So I'm going to go back to our notes, and it's going to be weird because I have 2 screens. There we go. Okay. Oh, it's doing something. Okay, I don't know what's happening. That's okay. All right, so the belt of stability. There's the fuzzy yellow line right here. Based on the fuzzy pink line that I just showed you. I still don't know why that... There we go. There we go. All better. Okay. So the purpose of the belt of stability... Well, first of all, the fuzzy lines, either the fuzzy pink or the fuzzy yellow line, are showing what nuclei are stable. So if we look at this graph a little closer, on the x-axis it shows the number of protons, and on the y-axis it shows the number of neutrons. And so we find a nucleus, and we are interested to see, first of all, is it radioactive or not? And if it is, what type of decay will it undergo? So which of those 5 choices will happen if I do the... when I predict what's going to happen. I said what's going to happen a whole bunch of times there. So what you do is you take your nucleus that you're interested in. I guess I'll make up one. Let's do... Well, my notes are not anywhere useful, so I'm totally making this up. I don't know if this nucleus exists or not. We're going to say 40... why am I not writing? 46... 17 chlorine. I want to know if this nucleus, is it stable or radioactive? And then if it's unstable, if it's radioactive, that means it's unstable. And if it's radioactive, we're going to talk through here in the next couple of minutes how I could tell what would happen to it. So if I'm going to do this, what I need to do is figure out how many protons and neutrons this nucleus has. So protons, it has 17. Chlorine always has 17, and it says 17 right there. Neutrons. Well, I'm going to take 46 minus 17, and I get 29. So that's the information I need to use this graph. So what I'm going to do is I'm going to go down to the x-axis, which is protons, and I'm going to find 17. Now it shows, 10 and then 20, and there's a 15 there. So we're just going to kind of have to estimate 17. Okay. And the neutrons is 29. So I'm going to go to the y-axis and go to 29. So I'm going to kind of go with, it's like close-ish to there. This was not an awesome choice, but There we go. That's what I'm going with where it is. So to me, it looks like it is not in that yellow fuzzy line. It's on the outside of that yellow fuzzy line. It's really close to it, but it's on the outside. So if it is not falling inside of that yellow fuzzy line or the pink fuzzy line in the other belt of stability, that means it is radioactive. So the belt of stability, that belt, that fuzzy line, shows everything that is stable. So every nucleus that's stable, when I use this graph, it's going to fall into that. So if it doesn't fall into that fuzzy yellow or pink line, that means it's unstable, so it's radioactive. So this is radioactive. Let's do 40, 20, calcium. Okay, so 20 protons, 20 neutrons. So 20 protons right here, 20 neutrons right there. That's definitely in the... Why does it keep making lines? I don't know why I'm asking you. It's not like... Well, maybe you do know. I don't know. So there-ish. That's... Yeah, not quite. Close enough. There-ish. Definitely inside that yellow fuzzy line. So this is stable, which means it is not radioactive. So this one that is radioactive, it's going to do one of those 5 types of radioactive decay. The calcium-40 that is stable is just going to hang out as calcium-40 for the rest of its lifetime, unless someone screws with it somehow. So it's not doing anything interesting. Okay, so what this graph, I mean, it obviously tells us if something is stable or unstable. So stable, not radioactive, or unstable is radioactive. And then we can also look at the graph to see, you know, what, like I said, we're going to learn how to tell if it's above the line, what does that mean? If it's below the line, what does that mean? So the reason why some things are radioactive and some things aren't, it obviously has something to do with the ratio of neutrons to protons, because that's what this graph is looking at. And it's all about the nuclear force. So if you think about an atom, the nucleus has the protons and the neutrons in it. Neutrons are just neutrally charged. They're just things hanging out. Protons are positively charged. And how does one positively charged item interact with another positively charged item? Are they going to be attracted to each other or repulsed or repelled? Well, they're going to be repelled. But the nucleus is this tiny, tiny space where all the positive charges and all the neutral charges are stuck together, which counteracts the idea that like charges repel. So the nuclear force is that force that's keeping the nucleus together, keeping the protons all stuck together. And that very much has to do with the number of neutrons. So there's this ratio of protons to neutrons. That's an important ratio. Now, on the belt of stability, either the one that I've got in the Chapter 21 folder or the one that's on the screen in front of us, there's a straight line, not a fuzzy looking line, but a straight line. In the one in the chart in front of us is red. It shows a 1-to-1 proton to neutron ratio. So it's showing for a nucleus that would have, for every 1 proton it has 1 neutron. So like calcium-40 is a perfect example of that. It's got 20 protons and 20 neutrons. So if we look at that red line, it's inside the belt of stability until, you know, for a while. The one on our, till about there is what it looks like. The one that I gave you, or the one that's in the folder, it stays within the belt of stability until about 20. So kind of just after 20, it kind of stops being inside of the belt of stability. So obviously a 1-to-1 ratio of protons to neutrons, it's good sometimes, but as we get above a certain number of protons, that stops being a good thing. So that the ratio of protons to neutrons isn't always the same. And if you think about it, it's because the more protons you have, you're going to need more neutrons to force those high number of protons to stay stuck together in this tiny space. It takes more glue to hold together these positive charges, the more positive charges we get. Because remember, their initial response is going to be to repel from each other, to get the heck away from each other. But these neutrons and this force are trying to hold them together into this really tiny, tiny nucleus. Okay. So that's what this is saying, that the neutrons are important in this stabilizing the nucleus. So it's this ratio of protons to neutrons is very important. So that's what I just said, that less than 20 and less, the proton to neutron ratio of 1-to-1 is super good. And above that, it's a bigger than 1-to-1 proton to neutron, or neutron to proton ratio, sorry. So it takes more neutrons for every 1 proton. It doesn't ever get to like 2 to 1 or anything like that. But it's up to like 1.5 neutrons for every 1 proton. Is kind of where it ends. Okay, so like I already said, the shaded area, the yellow or the pink, is the stable things, and everything outside of that. So we went back to our example of the chlorine, and it was, what was it, chlorine 29? I don't remember what I made that, but it was like here somewhere. It was above the belt of stability, so it was above this. So when we find a nucleus and it is unstable, and when we do the protons and the neutrons and we see where they land, they're up here above, okay, that means that they actually have too many neutrons in order to be stable. So it kind of seems like it's opposite, but it's kind of like it has too much glue and not enough protons. So the response then is going to be for something to, we need some sort of decay that's going to get rid of neutrons. So if we look at the types of radioactive decay from the last video, beta decay had a neutron breaking down into a proton and an electron. So that is the mode, that's the type of decay that will get this unstable nucleus what it wants. So if it falls above the belt of stability, it's going to do beta decay. So that, like I said, whatever it was, chlorine something, it's unstable, so it's going to do beta decay, because what that's going to do is get rid of some neutrons and gain some protons, and it's going to start leveling out that ratio of neutrons to protons. So it doesn't matter what it is. If it's above the belt of stability, you're going to tell me that it's going to do beta decay. If it's below the belt of stability, so down here, okay, what happens is it has too many protons and not enough neutrons. So we need to look at something that will decrease the number of protons. And there are 2 things. If we go back and look at the behind the scenes, what's going on, number of protons, and that is positron emission, because in that scenario, a proton breaks apart into a neutron and a positron, and the positron leaves. So that's getting rid of a proton and replacing it with a neutron, which would help towards this ratio. The other one is electron capture, because what happens in electron capture is that electron from the 1s orbital gets pulled in and it smushes together with a proton to make a neutron. So both of these get the desired effect. So there are ways to tell which one is going to be which, and I'm not going to hold you to that. If it's below the belt of stability, you're going to tell me that it's going to be positron emission or electron capture. I guess I should change and to or, because I'm not going to make you decide which one it's going to be. Okay. So we've talked, beta is above, positron emission or electron capture are below. Gamma isn't impacted by the proton to neutron ratio, because gamma is just straight energy. There's no protons or neutrons that are involved with that. But there's one that we haven't talked about yet. And that one that we haven't talked about yet is alpha. That was the very first one we talked about. Okay, so, but we figured out how to determine if something is beta or positron emission or electron capture. And again, we're not going to worry about gamma, because gamma is not related to protons and neutrons. So it turns out that in the chart that I posted on Canvas, the graph stops at 80. So it stops right here. All this is, oops, well, I just deleted a bunch of stuff, but all this is not there. The graph stops at 80. This one, it stops at 100, but if you notice, it actually stops plotting the nuclei, the little black dots are the real ones, right there. So it turns out that if anything has at least 84 protons, so greater than 83, so that's 84 and up protons, all of the nuclei with at least 84 protons are all unstable, because 84 is just too many freaking protons to fit into a nucleus. It's just not going to happen. So everything that's 84 protons or above is automatically radioactive. So greater than equal to 84 protons, 100% radioactive, unstable. So that's why I like my graph. The graph actually stops at 80, so I know it's missing out on 3 nuclei, and I think that the world's going to be fine with that. But it's a hint that, hey, look, it stops at 80. There's probably a reason why it stops at 80, because everything 84 or above is automatically radioactive. And it's radioactive because there's too many protons. There's just too many things. The nucleus is too giant. So the nucleus needs to get smaller, like as fast as possible. And the fastest way for something to get smaller of those 5 types of radioactive decay that we talked about is alpha, because in alpha, aren't we losing 2 protons and 2 neutrons at once? So everything 84 protons or bigger is going to be alpha decay. Buddy, hold on. So that's not on the belt of stability, but I would actually recommend, if you've printed out the belt of stability, why don't you write that on the bottom somewhere? Because it's all going to be there in that same spot. So when we're dealing with those big buddies, the 84 or greater, I mean, if we're talking about, like, uranium has, 92 protons? Doing 1 alpha decay is going to bring it down to 90 protons. That is still above the 84 mark. So just doing 1 alpha decay is not going to get that uranium atom down to where it's stable. So with many radioactive nuclei, 1 step isn't enough. What we talked about with that belt of stability, so like with this chart, lets us predict the first step. Okay. After that, I'm not going to hold you accountable to predicting what's going to happen after that. Okay. So after the first, so this will let you predict the first step. So you have your uranium-238. What's it going to do first? You could look at uranium-238 and decide it's got 92 protons, which is above 84, so it's going to be alpha decay, and you could tell me that. But then what I just want to talk about is the fact that that's not done. So this is looking at uranium-238, and this is showing what's called a radioactive series. Every single step that this uranium atom is going to have to undergo before it gets down to where it's stable. So it starts here, uranium-238, unstable, and it ends lead-206. This is when it's finally stable. So the radioactive series stops when it gets to where it's no longer radioactive. These often end at 82. Lead is a pretty common ending point for these very large radioactive isotopes because 82 is below 84. It's, relatively close to being below 84. And if there's lots of alpha decays going on, well, it's 2 protons less than 84, so kind of works out. So I would never, for this class, I'm not going to have you do this. I'm not going to have you start a radioactive series and go all the way through to the end, but I want you to be able to look at this. So the blue arrows, so like this and this and this, those represent alpha decay. So unsurprisingly, uranium-238 first does an alpha decay. That's what we'd predict. Okay, but then its next step is a little red arrow. The red arrows represent beta decay. Okay, so again, I would not say, hey, map this whole thing out from beginning to end. It's totally possible. I'm just not going to teach you how to do it. But what I could do is tell you, hey, uranium-238. First step is alpha decay. Second step is beta decay. Third step is beta decay. Write out the reactions for each of those. And then you would have to say, okay, uranium-238, 92. First step is alpha decay. And I would have told, well, that one you could have figured out on your own. We can write the balanced equation for that. 234 and 90 is thorium, right? Are you, bucko? Yeah, thorium. Okay. So that would be step 1. Step 2 is going to be beta decay. So I'm going to take the thorium, the 90-234 thorium, and the reason why I'm starting with that is because the uranium-238 is now gone, and it's going to do beta decay. So I can balance this, say 91 plus -1 equals 90, and 91 is protactinium. Okay. And then third step is beta decay. So I'm going to take the 234, 91 protactinium and do another beta decay. And this would be 90, 234, 90 is back to, wait, nope, I lied. I'm so bad at math. This is even a thing that I told you guys not to do. 92, 234, 92 is uranium because 92 plus -1 equals 91. So this is what I could do. I could tell you step 1, do alpha. Step 2, do beta. Step 3, do beta, and have you write out those reactions. I wouldn't say, okay, uranium-238, go. How does it get there? You're not going to know the answer to that. But radioactive series, this is just real life for these really large nuclei. Okay, so before I go to the next slide, hopefully we're feeling okay with our belt of stability. And again, you're never going to have to like in no situation ever would anyone ask you to memorize the belt of stability. That's just not a thing. Okay. But it's using the belt of stability to determine what the first step would be. And then understanding that a radioactive series is just all the steps that it takes for it to get stable. Okay. So hopefully we're feeling good with that. Now, backstory. So chemists were nerds. All right. It's not a surprise. I'm guessing you know this about chemists and many scientists. And so we have these academic journals that, that new things done in the lab, new procedures, new evidence are posted in. We also have, in the American Chemical Society is the group in America, based on the title of that, hopefully we're not surprised, that chemists subscribe to. They're part of this professional organization, and we get either, it used to be paper magazines, kind of magazines every week, but now it's emails. And sometimes in there they include jokes that only chemists would probably find funny. And so this is one of those jokes. It's actually very, very old. It's not a recent one, but you guys will now understand this joke. Whether you think it's funny or not, I don't know that I want to know about that, but I thought it was funny and I giggled and I found it and I put it in the PowerPoint slides because it made me happy. So that's what we're getting ready for. Are you ready for this? So at the home for old Adams, so there's two old wrinkled grandpa Adams hanging out right there. And at the bottom it says, "When I was young, I used to feel so alive, so dangerous. In fact, would you believe that I started out life as uranium-238? Then one day I accidentally ejected an alpha particle, and that's where it all began. Now look at me, a spent old atom of lead-206. It seems that all my life since then has been nothing but decay, decay, decay." Get it? Because it did alpha decay and then beta decay. It's fine. I think it's funny. So it's that, only as, well, whatever it is. Okay, moving on. So when we're talking about stable and unstable things, outside of the belt of stability, because, although you should always have it in your back pocket, so that way, you run along and you pick up your radioactive nucleus and you want to know what's going to happen, you can pull out your belt of stability and figure that out. But sometimes that's just not an option. So there are these magic numbers, these numbers of protons and or neutrons, that if a nucleus has one of these magic numbers of protons or neutrons, it's much more likely to be stable. So these magic numbers are the numbers that predict stability. I am not, again, nor is anyone ever going to expect for you to memorize these unless you become, unless whatever job you're in is dealing very much with radioactivity, in which case maybe someone will expect you to memorize these magic numbers. But again, I'm not holding you to memorizing these magic numbers. But what I want us to look at is the table over here. What they did was they took every single stable isotope of every element that we know about. So the ones that were in that belt of stability, like all the little dots that represent the stable ones. And they broke them into 4 categories. They broke them apart and figured out how many protons and neutrons they had. And then if it had an even number of protons and an even number of neutrons, they put them in this first category. If they had an even number of protons but an odd number of neutrons, they put them in the second category. Third category was an odd number of protons and an even number of neutrons. And the fourth category was an odd number of protons and an odd number of neutrons. And if you look at these categories, one of these categories had the most stable isotopes in it. So again, all of these are stable isotopes. But the most common, like the one with the most in it, was an even number of protons and an even number of neutrons. Now, the second two had one even and one odd. They broke them into the 2 different categories. But if I were to put those 2 together and say, okay, these are the nuclei that are stable and have an even number of protons or neutrons and an odd number of protons or neutrons, and we're not worried about breaking those apart, well, those 2 account for almost all of them. Having an odd number of protons and an odd number of neutrons, only 5 stable isotopes exist that fall under that category. So in other words, Things that have odd numbers of protons and neutrons are less likely to be stable. So if you have an even number of protons and neutrons, or even an even number of protons or neutrons, you are much more likely to be stable, not you, a nucleus, than if we have odd numbers. So in other words, instead of memorizing these magic numbers, what I want you to know is what's in that purple box. Even numbers are more likely to be stable than odd numbers. And again, the even numbers, what I'm talking about is the number of protons and neutrons. So again, even number of protons and neutrons, pretty likely, at least more likely to be stable. Even numbers of at least one of those two things, yeah, has a chance of being stable. Odd number of protons and an odd number of neutrons, yeah, that sucker's probably not stable at all. Okay, so just know that even numbers are more likely to result in stable things than odd numbers. Okay, so we now know how to identify, what's going on, if a nucleus is stable or unstable, and predict the first step of its decay. What we're going to look at, so that's all, everything up until this point has been naturally occurring radioactive processes, right? We find a nucleus, it already exists, it's unstable, what's it going to do? So starting here, we're going to be looking at forced nuclear processes. So not naturally occurring things that we forced to happen. So particle accelerators are the labs, basically, where we can force radioactive or nuclear processes to occur. They don't have to necessarily be radioactive for me to force it to happen. It could be a stable nucleus that's being forced to react with a stable nucleus or something. So a particle accelerator is huge. They're miles long. They are circular tracks. There are only so many of them in the world. I'm going to have a list of those here in a little bit. And what happens is inside the particle accelerator, it's under vacuum. So there's nothing in there. Like there's not even air. It's under vacuum. Okay. And they're able to put beams of nuclei. So like a beam of protons. So not just one proton, but like a string of protons. And then these particle accelerators can do kind of what their title says. They can take the particles and accelerate them, make them go really fast, and then deliberately have them bombard another type of nucleus. So maybe these protons can be accelerated and smushed into a bunch of nitrogen-15 nuclei or something. Because they're going so fast, we're forcing them to interact with each other. Again, this is not a naturally occurring process. This particle accelerator is forcing these two nuclei to interact with each other, and then we can see the results of them. As much as I would love for you to have an experience to do this, I would love even more for me to have an experience doing this, but it's like thousands of dollars an hour to be able to use a particle accelerator. So this is like, you're as close to a particle accelerator as I've ever gotten to. Sorry, buddies. So these are called nuclear transmutations. Nuclear transmutations are forced nuclear processes inside a particle accelerator. And these, what is it with this thing? Accelerator. These are going to typically look like, I don't know why these are the letters that I chose, but something and something are going to smush together and we're going to make something and something. So unlike the radioactive ones where we had either one reactant and two products, or there was one scenario where we had two reactants and one product, these look kind of more similar to, like a metathesis type of reaction as a chemical reaction, but yet not still, it's still a nuclear reaction. But we're going to always have two things at the beginning, because we've got the little tiny particle that we're accelerating, and we're going to smash it into the bigger nucleus. And yeah, so the elements kind of, everything with an atomic number of 110 or greater are called transuranium elements. These are elements that were made in a particle accelerator. They are not naturally occurring elements. They were made by forcing more protons into the nucleus. They only exist for a fraction of a second, and there's some sort of rule on how long they have to exist before we can say that they're a new element, because if they immediately break down, then did you really make something new? So these nuclei, 110 and greater, most of those have only recently been named because they were created in a particle accelerator. Okay. So this is what these nuclear transmutations look like. When we're writing their equations, the rule for how to balance them hasn't changed. All that's going to be different is that we have two things at the beginning and two things at the end. We might see coefficients with these, and we'll look at that. So these are some examples. So the first way is the way I like to write them. They look more like an equation. I like, just a reminder, I'm not all fancy with the alpha signs, and with protons, I like to do 1,1p is how I like to write them. 11H was one of the examples I gave you guys, is what a proton could stand for, because a hydrogen 1 is just a proton. But anyway, if we look at this equation, I'm just going to prove that it's balanced. 7 plus 2, isn't that 9? 8 plus 1, that is also 9. 14 plus 4 is 18, and 17 plus 1 is 18. So this is still balanced. It's just, it's two things and two things. So the shorthand notation for the fancy nuclear chemists look like this down here. So this is for the same reaction that's in number 1. So what they do is the target nucleus is the one that's not being accelerated, the one that's going to get smashed into. It's the bigger of the two initial things. So of these two, nitrogen's the biggest one, so it goes there. Then the smaller one that's going to get smashed into it goes right here. It's called the bombarding particle because it's the one that's going to be accelerated around the particle accelerator and then smashed into it. They're going fancy here. Instead of writing 1,1p, they're writing alpha for that. And then in circle, whatever. Okay. No, sorry. Not alpha. What would be 1,1p? It would be 2,4,2 helium. And then over here, the products, they're going to go with the second two things. The biggest one goes on the outside, and the smallest one goes on the inside. So the small ones go inside of the parentheses, and the large ones go on the outside of the parentheses. So in this, the comma is kind of like an arrow. So that's showing the division between the left-hand side and the right-hand side. So this and this arrow, this and this. So the bombarding particle, again, means the one that was accelerated. On the product side, the ejected particle, so when these two things smash together, just like with any collision, think with like a car accident. When two cars are going fast enough and they collide, pieces fall off the vehicles. Like when they collide, not only is there damage done to the vehicles, but usually hubcaps fall off, or like rear view mirrors or whatever, things fall off. So that's what this buddy is, the ejected particle. It's the random crap that fell off when they smashed together. And then the thing on the outside is the product nucleus, so hopefully what they were trying to make, or it is what they made, whether or not it was what they were trying to make. Okay, so with these, if I would ask you to write the equation, we're going to just practice this. I would have to give you 3 of the 4 things if I wanted you to predict it. So I'm going to say, I'm making this up, so hopefully this works out. A 14,6 carbon is going to be bombarded with a 1,0 neutron. So this is the bombarding particle that got accelerated. And then on the other side, I'm going to tell you, that a proton fell off, and I want us to predict what was the nucleus that we made. So if we've got to balance this, that total is 6. So the total on the other side needs to be 6. So doesn't that mean that has to be 5? The total on this side is 15. So the total on the other side is 15, so that means this one has to be 14, because there's a 1. So 5 is boron. So we made boron 14. Okay, so let's do one where we have coefficients. So let's go with 147, 50, 10. And I bombarded it with a proton. And what happened is, on the other side, we broke off 4 neutrons, and then we're trying to figure out what the heck is going on here. So 4 neutrons, we could either write it like this, or with a 4 out front. But what you have to be careful with is that's going to impact the number on the top. So, okay, let's start out with bottom number. The total on this side is 51. The total on this side is 4 times 0 so far, so that's 0. So doesn't that mean this one's going to be 51? Now the total on the top over here is 148, and the total on the top over here so far is 4. 4 times 1. So it needs to be something plus 4 equals 148. So 144. 51. Antimony. Okay, so again, I would be giving you 3 of the 4 things, and you would be balancing it. If there's a coefficient, just multiply that by the numbers, the mass number or the atomic number when you're balancing. Okay. So this is just, some people get super excited about this and want to learn more. So just in case you're interested, these are particle accelerators. These are some of the particle accelerators if you're interested in looking them up. They can accelerate protons and larger things to close the speed of light, which is crazy because that's that 2.998 times 10 to the 8th meters per second, super duper fast. Okay.